but not, now B is this, put it in here, so not B is not A, here, this is this. But not B, what is B? B is not P, so you've got not P, that's P. Okay? And this is not A, but what's A? A is not Q, so you've got not Q. Well, that's just Q. So not P gives you not Q, so in other words, P is Q. That's what you want. That's what you're trying to prove. Now, if you if you didn't follow that, just wind it back and go through as many times as you need to follow the logic. Okay? So, to prove something by contradiction of the form, if P then Q, you assume not Q, and from that you deduce not P, but you know P is true, and you've deduced not P. Therefore, your not Q must have been false. So what is true is not Q, which is Q, which is what you want. Okay, so let's do a few more examples of proof by contradiction. RAA, reductio ad absurdum. Let's let's try this one. So let's say A is an integer, okay, and A squared is even, implies A is even. Let's try to prove that. Okay, so let that be statement P, and this is statement Q. Okay, so if the square of an integer is even, therefore the integer itself is even. So how do you actually prove that? And let's try to do it by contradiction. All right, so let's assume the opposite. So assume A is odd, right? So A is an integer, so it's either even or odd. They're the only two possibilities for integers. So if it's not even, it has to be odd. Okay, so A is odd, and therefore A can be written in this form: 2 plus n plus 1. Okay, that's an odd number. Now, if you square that, square this thing, 2n plus 1 squared, that will give you 4n squared plus 4n plus 1. Okay, so that's 4 into n squared plus n plus 1. Now this, you can see, that's an even number, right? That has to be even, because this is an even number. Okay? So you have an even number plus 1, so that whole thing is odd. Okay? So A squared now is odd. But you started with, you began with, one of your premises was A squared is even. So this is not P. It's the opposite. Okay? So you've got yourself a contradiction. Therefore your original your assumption here, when you're trying to prove Q, and by using proof by contradiction, you assume the opposite, in other words, not Q, and you got the contradiction, so you got P and not P, so therefore you reject this. So the case, it's not Q, in other words, Q, from this logic. Okay? So what's Q? Well, A is even, so you've proved it. Right? So if A squared's even, then A is even, using this kind of reduction to absurdity, RAA in Latin, reductio ad absurdum. Right, let's do one more before we move on. There is no maximum prime number. How can we prove that? It's a famous proof, again from the ancient Greeks, 2,000 years old. So let's again use the proof by contradiction. So now we've known for 2,000 years that the number of prime numbers, remember a prime number is an integer that has no factors other than itself and 1. So the prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and we're trying to prove that there is no maximum prime. Right? So in other words, the number of primes is infinite, just goes on forever. So how do you prove that? How do you prove there's an infinite number of primes? If you think about it, it may not seem obvious, but it can be done using a proof by contradiction. All right, so assume the opposite. And what is the opposite? That there are a finite number of primes. There's a limit to their number. So let's call the maximum, the biggest prime, P for prime, P max. Okay, that's the largest prime. And let's create a number which is the product of all these primes. Right? So it's 2 times 3 times 5 times times P max. Okay, so by definition, I'm going to put 3 bars here. That number, an integer, of course, is the product of all the primes. All of them, up to the maximum prime, because we're assuming the opposite of what we're trying to prove. That there's no maximum prime. That the number of primes is infinite, goes on forever. Okay. All right. Now let's add 1, because that's a trick, ingenious little trick. So we multiply all the primes together and then we add 1 to them. So this number n, you cannot divide it by 2, right? Because if you divide this number by 2, that number has a factor of 2. Yeah, there it is. But n is this number plus 1. So n, you cannot, here, I'll write it in this form. N does not have 2 as a factor, right? Because you always have this 1 left over. Okay? So if I mod that by 2, modulus, I don't get 0, but I get 1. And similarly, n mod the next prime also, you cannot divide n by 3, and so on, all the way down. So n mod p max also not, this doesn't give you 0. So you cannot divide n by p max. Now, now you've got a real problem. Now, in pure mathematical proofs, if you've already proved something elsewhere, some other time, then like if some other mathematician, say, has proved if P is true, then Q, so if that's been proven, you can take that result and use it in your proof. Right? Now, there's a word for that. If you have some smaller proof that you use in your proof, that smaller proof usually gets the label lemma, L-E-M-M-A. Okay? So a lemma is a kind of minor proof, a part proof that you use in your bigger proof. So in your theorem. A theorem is a statement that you're trying to prove and its proof. Right? That's a theorem. Okay, so a lemma